Hello, welcome to this lesson in the linear algebra tutor. We're finally going to start talking about eigenvectors and eigenvalues. I'm giving you a little motivation, trying to get you a little bit of interest in how these might be useful to you. Now we're going to actually jump into it. So we'll just jump right on into it, which typically we'll see in a book. This is called the eigenvalue problem. All right, basically, if you have a matrix A times some column vector x, which these are lots of unknowns, don't forget this is a matrix equation, and it's equal to what we call lambda x. That's it, ladies and gentlemen. That is the eigenvector problem. If you understand everything there is to know about this equation, then you understand eigenvectors and eigenvalues. So it looks deceptively simple. Let's jump into a little bit of the details. Okay, this x here is called the eigenvector. And this lambda here is called the corresponding eigenvalue. Basically, the way that this works in real problems is in order to find the eigenvectors, you have to first find the eigenvalues. Those are just numbers, okay? Once you find the eigenvalues, then you can find the corresponding eigenvectors. And that's why I say eigenvectors and values go together like peanut butter and jelly. For a given eigenvalue, which is just a number, you get a corresponding set of eigenvectors. For the next eigenvalue that you have another corresponding set of eigenvectors. And remember, these eigenvectors, for instance, for principal axis of rotation, gives you the direction of symmetry in objects. So that's just one example, but I think it's good to have some grounding. Let's take a little bit of a closer look at this. The eigenvalues, these are just scalars. Right? And so the eigenvector, I'm not going to write it there, but it's a vector. The word eigen it's a German prefix. Don't worry so much about what that means, but basically these are special vectors associated with this matrix and special values associated with this matrix. What do you think makes them special? What it's basically saying is, if I take the matrix A and I multiply it by an eigenvector x, okay, then when I get on the right-hand side is the same eigenvector but multiplied by a scalar. So it's a special solution of the matrix where when you put that vector into the left-hand side of the equation, you get the same vector back but just scaled by a value, the value that we call the eigenvalue. All right? That's why it's called eigenvalues and eigenvectors. So make sure you understand that. Just conceptually what it is a special solution of this equation such that if you stick it back in the left, you get the same thing out but scaled times a constant. And remember, these are vectors. They point in the same direction, right? X and x point in the same direction. And even if you take x and multiply it by a number, it's still going to point in the same direction. So what it is a vector that points in a certain direction. You stick it in the left, you get back another vector that points in the same direction, but it's scaled, which means it's maybe longer or shorter. Okay? For every eigenvalue lambda, there is a set of non-trivial vectors x that we call eigenvectors. I want to say that out loud because I have it written on my paper. So now that you have the general idea of what the eigenvalue problem is, ultimately what we're going to figure out how to do soon is how to calculate these eigenvalues and how to calculate the corresponding eigenvectors. But before we get to that, we're going to do a simpler problem. I'm going to give you a matrix A, in this case 1, 6, 5, 2, and I'm going to give you a vector x1, 6, negative 5, and I'm going to ask you, is x1 an eigenvector? So ultimately, you need to be able to have a matrix and calculate the eigenvectors and eigenvalues. We're not doing that yet. We're going to take baby steps. I'm going to give you a matrix, and I'm going to ask you, is this an eigenvector of this matrix? And you have to answer yes or no. Well, the way you figure it out is you go back to your definition. Ax is lambda x. So let's stick it on the left-hand side. A is 1, 6, 5, 2. And the test vector that we have, the potential eigenvector, is 6 times negative, or 6 and negative 5. Now we need to do some matrix arithmetic here, so we're going to go over and down. Okay? So 1 times 6 is 6. 6 times 5 is negative 30, since it's negative 5, so I have a negative 30 here. And then going over and down, 5 times 6 is 30, and 2 times negative 5 is negative 10. So this matrix, when I plug in the potential eigenvector, I get negative 24. And on the bottom, I just get 20. And the question is what I get when I plug this in the left-hand side, is it a multiple of the original vector? The question is, can I take this original vector, which is 6 and negative 5, And can I multiply it by something to give me what I have just gotten on over here, negative 24 and 20? Is this possible? The answer is yes. What if I multiply by negative 4? Negative 4 times 6 is negative 24. Negative 4 times negative 5 is positive 20. Because there is a relationship here, we can say actually two things as a result of this. Yes, 6, negative 5 is an eigenvector. Here's a bonus question for you. What is the eigenvalue that corresponds to this eigenvector? Well, lambda, which is the eigenvalue, is what sits in front on the left hand, in front of the vector over here. So we say that in this case, lambda is negative 4. Make sure you understand this. What we're saying is this is the eigenvector equation. In order for eigenvectors and values to be solutions, they have to satisfy the eigenvalue problem. So we take our potential eigenvector, we stick it in the left-hand side, and we get this. And we have to ask ourselves, is what we calculated here a multiple of the original vector? And we find out that it is a multiple of the original vector. The multiple happens to be negative 4. So with the eigenvalue ends up being negative 4, the eigenvector ends up being this. All right, so again, we haven't gotten to the full glory of the problem. We haven't calculated the eigenvectors from scratch or the eigenvalues from scratch. But still, these kinds of problems are really useful because they teach you the basic ideas of what an eigenvalue is. So let's say we had the matrix 1, 6, 5, 2. And we have a potential eigenvector, x2 is 3, negative 2. And I want to know, is this an eigenvector of the problem or of this matrix? So we check it out. We say, well, is AX equal to lambda x? The matrix is 1, 6, 5, 2. The test vector in question is 3 and negative 2. What do we get? 3 times 1 is 3. 6 times 2 is negative 12. 5 times 3 is 15. 2 times negative 2 is negative 4. So what I end up getting here, 3 minus 12 is negative 9. And 15 minus 4 is positive 11. So what I end up getting is negative 9 and 11. That's what happens when I plug this into the left-hand side. So the question is can I find a multiple of this original vector that will give me this? So the original vector is 3, negative 2. Lambda times this. Can this be equal to negative 9 and 11? Can I take a multiple of the original vector and have it equal what I've already calculated over there? Ask yourself that. Well, how do you get 3 to be negative 9? Well, you have to multiply it by negative 3. But if I multiply this by negative 3, there's no way it's going to be equal to 11. There is no multiple that I can multiply my original vector by to give me what I just calculated. So there's no way that this vector, when I put it in here, can be a scalar multiple of itself when I run it through this matrix. So, not an eigenvector. So there's no eigenvalue associated with it. There's no eigenvector. There's nothing special about this guy. This is just another vector. It's a test we ran. Failed the test with flying colors. Now those were 2 by 2 matrices, but the exact same thing holds for larger matrices. What if I have 2, 2, 1, 1, 3, 1, 1, 2, 2, and I want to test this vector and see if it's an eigenvector. Negative 1, 1, 3. Okay, so how do I do it? Well, I got to run it through the eigenvalue or the eigenvector equation. AX is lambda x. And I have to test that for equality. So when I put it in here, 2, 2, 1, 1, 3, 1, 1, 2, 2, and I just write down the matrix, negative 1, 1, 3. Let's do this multiplication here. So what I will have is 2 times negative 1 is negative 2. 2, I'm going to go down like this. 2 times 1 is 2. 1 times 3 is 3. I go over and down here. This gives me a negative 1. This times this gives me a 3. This times this also gives me a 3. And then I go over and down. This gives me a negative 1. This gives me a 2. And this gives me a 6. So when I run through all of that, this goes away, giving me only 3. This is going to be a 2 plus 3 is 5. And then this is going to be 1 plus 6 is 7. So I get 357, 357 there. And the question is this a scalar multiple of my original vector? Well, such that I can multiply it by an eigenvalue and get it. So to formalize that, the question is, can I take 3, 5, and 7 and write it as some kind of multiple of my original vector, -1, 1, 3. Is there any way you can do that? Well, if I multiply this times, to get 3, I'd have to multiply this by -3, right? -3 times -1 to give me that. But if I multiply by -3, there's no way I'm going to get that. And there's definitely no way by multiplying by -3 that I'm going to get that. So this vector is not an eigenvector. All right, so you see the idea here. I want to do one more with you. These are really great little test questions or quiz questions, and I'll give you a little bit of a preview. This one will be an eigenvector. There's no way you can tell ahead of time until you run it through and test it. So 2, 2, 1. In fact, this is the same matrix. We're going to use the exact same matrix. 2, 2, 1, 1, 3, 1, 1, 2, 2. And the potential eigenvector that we're testing is 1, 1, 1. Okay, how do we figure that out? We run it through the eigenvalue problem. AX is lambda x. All right, so the matrix we have is 2, 2, 1, 1, 3, 1, 1, 2, 2. We're testing it by multiplying it by the potential eigenvector. And what do we get? Well, we're going to have 2 plus 2 plus 1. Pretty easy to multiply when you do this. It's going to be 1, 3, 1. And then this across and down is 1, 2, 2. And so at the end of the day, I'm going to have 5. And then I'm going to have 5, 6. No, 5. This is going to be 5 as well. And then I'm going to have 5 here. And the question is this a linear combination of this? And of course, you can see right away that it is. The way you write that is lambda times my original vector. Is this equal to what I just calculated? 5, 5, 5. And the answer is yes, lambda has to equal 5. If I put a 5 here and multiply by each of these, I get what I have calculated here. So this is the eigenvalue, and the eigenvector that goes along with it is this original vector. 1, 1, 1, and we say this is an eigenvector. So now you understand why I say eigenvectors and eigenvalues, they go together like peanut butter and jelly. For every eigenvalue you have, you're going to have one or more, as we'll see, eigenvectors and so on. So the way you test for that is you run it through and see if what you get can be written as a multiple of your original value. If you can, then you've identified the eigenvalue and you know that your test vector is actually an eigenvector. So in this section, we've introduced the concept of what eigenvalues are and what eigenvectors are. But we haven't really learned how to find them from scratch. We've just done some tests. What we're going to start to do in the next section is introduce the method in which you actually go and find the eigenvalues of a problem and the eigenvectors.